The objective of this video is first to quantify the harmonics in the cumulative air gap field and current linkage that are created by our stator winding, and second to relate these harmonics to torque ripple and rotor losses for three-phase machines. This video exclusively considers a three-phase machine. What we're going to do in the first portion of the video is write out our expressions for current linkage that we have calculated due to our winding factors, and we're now going to consider all three phases. So the total current linkage that is acting in the air gap of our machine is due to the sum of the current linkages of each of our phase windings. We are then going to make calculations of this cumulative current linkage for different harmonics in our phase current linkage waveform. So let's begin by recalling the expression for air gap current linkage in terms of our winding factor. And you can see that I've written an expression right here for phase U current linkage at harmonic V. So in this notation, U refers to the phase and V refers to the harmonic index. So the current linkage created by phase U with harmonic V is going to be 2 over pi times our number of turns that are in series times our number of coils divided by V times P, where V is our harmonic index and P is our number of pole pairs, times our winding factor for this harmonic index, times the phase current, and then times the cosine of Vp times alpha, where alpha is the angle within the air gap. And this expression should be familiar to you. We were just recalling this from our previous video on relating electric loading to winding factors, and it's written in a slightly different form, but you should be able to plug quantities in to get it into this form. And to make our lives a bit easier, for this video only, we're going to define the following constant. So we're defining theta prime to be this portion of our expression, so we can save ourselves from having to write that out numerous times. And we can take this current linkage expression and write the expression for an equivalent linear electric current on the inner bore of our stator that will create this same current linkage. And to construct this expression, I just recognized, going back to our electric loading unit and our discussion about rotating equivalent current densities, that the linear current density, the equivalent current density in the inner bore of our stator goes by the sine of Vp alpha, whereas the current linkage goes by the cosine of Vp alpha. And then the magnitude of our linear current density is going to be Vp over R times the magnitude of our current linkage. And so this is something that we developed back in our machine design sizing unit when we talked about equivalent current densities. And so we can more generally write this as follows. And so you can see I'm taking Vp over R times our current linkage, and then our current linkage is phase shifted by pi by 2 Vp, which is what turns this cosine into this sine. And then I can do the same thing for the remaining phases. And so we've got phase V and phase W, which are phase shifted by 2 pi by 3, and then 4 pi by 3 at the electric frequency. And we talked about this when we talked about harmonics in our current linkage, when we talked about the way that we represent harmonics in machines for higher numbers of poles. And we can recall what our current waveform should be in order to produce symmetric rotating field for a three-phase machine. So we want to have three-phased balanced currents whose angle varies with our rotor position and this phase angle phi. And so in our machine design sizing unit, we developed these expressions in order to produce torque, where torque was proportional to the sine of phi. And in our winding factor, introduction to winding factor, we related our winding factors to our current linkage to this expression. So this is all review. Let's now go ahead and move forward by considering the total current linkage that acts in our air gap, which is going to be the sum of these quantities. And again, the reason that we are doing this is that current linkage can then be used and converted into our total equivalent linear current density, so we can use it for a torque calculation, and it can be converted to our total equivalent field that's in our air gap and we will talk about how that relates to losses in the later part of this video. And so again, we're calculating this by summing up these three quantities. So here's phase U, phase V, phase W, and our total current linkage we're referring to as theta S, comma V, where S means the stator current linkage and V is harmonic V. And we can convert this cumulative current linkage to our equivalent linear current density in the manner that we just discussed up above, right here. And then we can convert it to our normal magnetic field in our air gap, our radial magnetic field, using the result that we derived back in our equivalent circumferential current density unit, which is that our current linkage is divided by our air gap and multiplied by mu naught. And so now what I'm doing is I'm going to plug in our expressions for each of these phase current linkages, and I'm going to add them up and work on the math. So you can see already I've written out our current linkage due to phase U has got this cosine VP. So I pulled these terms out and I put them out here in front. And then my cosine sits inside here, and it's multiplied by IU, which has got I hat times cosine of alpha W. So here I hat came out because it's common to all three of these. And then cosine of alpha W is sitting right here. So I'm going to do this for phases U, V, and W, and then I'm going to work on simplifying the math to get this into a workable expression. And so you can see I've got phase U right here, phase V right here, and phase W over here. And now I'm multiplying these cosines together. And when you multiply two cosines together, you get the sum of two cosines with their arguments either added or subtracted, and there's a 1/2 term. So I pulled the 1/2 out in front, and then here I've got my expression for the cosines added and subtracted for phase U. And now I've written this out in terms of a phasor notation. So I'm trying to combine all these cosines and sines, and so you can see that I've used our typical phasor notation. We're taking the real part of this complex quantity in here, and this complex quantity, all of these cosines have a VP alpha. So I've pulled that out in front, and then you can see that the argument either goes by a set of negative alpha W. A set of negative alpha W values, which is this right here, or it goes by a set of positive alpha W values, which are these terms, and that corresponds to these terms right here. And so what we can say is that this looks like the sum of two waves that are rotating in opposite directions. This top complex quantity up here is the polar notation for a phasor that's rotating in the counterclockwise direction, and that's the direction of our rotor's rotation. And we know that this is rotating in the counterclockwise direction because alpha W is the opposite sign of this argument over here. So if we take the real part of these expressions multiplied by each other, we get the cosine of VP alpha minus alpha W, and that is the equation of a wave which is traveling in the counterclockwise direction. Alpha is increasing. And similarly, we can see that these bottom terms represent a wave that is traveling in the clockwise direction. So this is interesting. Remember, we had talked about the whole goal of our winding design being to produce a current linkage that travels in the counterclockwise direction in sync with our rotor. But here we can see that we've got this expression for our current linkage, and there's actually two waves. One wave that's traveling in the counterclockwise direction, which is what we want, and a second wave which is traveling in the clockwise direction. So let's unpack this a little bit further. Let's start by considering the V = 1 harmonic, our fundamental harmonic. And if we first just look at this term up here, and we plug in V = 1, we can see that it reduces down to this expression here, which is just simply 3 times e to the negative j alpha W. And then if we look at our clockwise direction, If we look at the clockwise direction and we plug in v equals 1, I see I have a mistake. This should be a plus 1. If we plug in v equals 1, we're going to get e to the j alpha w plus e to the j alpha w minus 2 times 2 pi by 3, which gives us this, alpha w minus 4 pi by 3. And then e to the j alpha w minus 2 times 4 pi by 3, which is equivalent to e to the j alpha w minus 2 pi by 3. If you just take a 2 pi out of that. And that sums to 0. So we can see that for our fundamental harmonic, we have exactly what we want. We have a wave that is going to be traveling in the counterclockwise direction, and no wave traveling in the clockwise direction. And so everything in here is going to become 3 times the cosine of jvp alpha minus alpha w. So this is our phasor that resides in here. And so you can see what I've done here to construct our current linkage expression is that I've taken this and I've plugged in v equals 1, and then I've multiplied it by 3 from here, and then I've taken the real part of all of this, which gives us the cosine of p alpha minus alpha w. And you can go back to our lecture video that introduced electric loading related to winding factors, and you can come up with the same expression from that analysis. So this is nothing new at this point. And then, of course, we can also write this in terms of our current linkage, not current linkage, but linear current density. And you would get this expression right here. And if you plug in our definition for theta prime, which we just wrote up here, and this is just for this video, you'll get the same expression for current linkage as we derived again in that same video where we introduced current linkage in terms of our winding factor calculations. So this is good. We're reproducing results that we know and are comfortable with, and we can make a few more comments here. And we can say that what we want to do is evaluate the speed that our wave is traveling at. And so we can notice that our wave always has to peak when the argument of this is 0. So that is to say that when alpha equals alpha w by p, because we want the argument of that to be 0 to find the location of the peak of our wave. And if we assume that alpha w is omega t, where omega again is our electric frequency, we can conclude that our wave travels at the derivative of alpha, which is omega by p. And this is again an expected result. We know that our rotor is going to be moving at omega by p if it's a synchronous machine, and so therefore we want our current linkage to be traveling at that same speed for our fundamental component. So we've just proven what we knew should be the case anyway, but we're doing this so that we get our feet on solid ground so we can now consider what happens for harmonics that are not at v equals 1. And the key points here is that the wave is traveling in the counterclockwise direction, and it's got the speed of omega by p. And so what we're going to do now is we're going to construct a table of the different harmonics and which way the wave travels and at what speed it travels. And so you can see I've set this table up so that we'll be calculating the first 7 harmonics. And each of the columns of the table is to indicate a key quantity. So right here, we're going to be calculating the counterclockwise portion of this expression up here. So I've pulled the negative j alpha w out, and we're just going to strictly be calculating the phasors of this and this plus 1, so that we have the quantity of those phasors multiplied by this. And then over here we're going to do the same thing but in the clockwise direction. And so this should be alpha w. And then we're going to summarize our field speed, the rotational speed of our current linkage. And then we're going to write an expression for the magnitude of our current linkage and then the magnitude of our equivalent linear current density. So let's get started. V minus 1 is going to be 0, and this first entry is actually just summarizing the quantities that we wrote up here, which we've already calculated. And so for the counterclockwise direction, we need V minus 1, and that's 0. And then you can see that our phasors multiplied by e to the negative j omega are just going to be all 1s. And then moving to the right, for the clockwise direction, we need v plus 1. That's going to be 2. And then our phasors, in this case, are going to be 1 plus e to the negative j 4 pi by 3 plus e to the negative j 2 pi by 3. And that equals 0. And so we can see that our speed, in this case, is going to be omega over p in the positive direction. And then we can complete our expressions for our current linkage and our equivalent linear current density. And next we'll do this for v equals 2. So in this case, v minus 1 is 1. And we can write out our phasors, which we're going to be plugging in here. So we're going to have a 1 plus e to the negative 2 pi by 3 plus e to the negative 4 pi by 3. And we can do the same thing for our clockwise direction. And now we notice that we only have the clockwise field left. Our field is going to rotate at the speed of omega by 2p. And we can see that because in this case, this argument is 2p alpha. For v equals 2, this is 2p alpha, and therefore our speed is going to be slower. It's going to be omega by 2p, but in the reverse direction. And so we can plug in this for our expressions for our current linkage and our equivalent linear current density. A couple changes to point out to you. Whereas in our fundamental, we had just a p in the denominator. Now for our second harmonic, we have a 2p in the denominator. And then we have a 2 multiplied by our angle alpha. That was, again, a result of this up here and this over here. And then the direction of our rotation is in the clockwise direction. We have a plus alpha w. So now notice that our linear current density and our current linkage scale differently as we go to higher harmonics. The current linkage has got this v in the denominator, so when we go to higher harmonics, it decreases. Whereas our current linkage does not have v in the denominator, so it strictly stays tied to the value of our winding factor at that frequency. And so now I will complete the rest of the table. Okay, so we now have a complete table, and let's highlight some of the salient points. Our fundamental harmonic behaves exactly like we'd expect. We produce a wave traveling in the counterclockwise direction at the speed of our rotor. Our second harmonic produces a wave that travels in the reverse direction at half the speed of our rotor. Our third harmonic actually produces no wave at all. We've commented on this before, that for a three-phase system, the third harmonic winding factor does not matter. It will produce no field. And so we see that that is indeed true here. Our fourth harmonic resumes traveling in the counterclockwise direction, although at a much lower speed. Our fifth harmonic travels in the reverse direction at even a lower speed. Our sixth harmonic does not exist. It's a multiple of the third harmonic. So we can say that all multiples of the third harmonic will not exist in our cumulative fields. And then our seventh harmonic resumes traveling in the counterclockwise direction, but again at a much lower speed. So we can see that we have this pattern. We first produce a wave that travels in the forward direction, and then we produce a wave that travels in the reverse direction, and then we produce no wave at all. So harmonic 1 is in the forward direction, 2 is in the reverse direction, 3 does not exist. Harmonic 4 is again in the forward direction, harmonic 5 is in the reverse direction, and harmonic 6 does not exist. And this would continue so on and so forth. So what is the point in all of this? Well, first let's comment that we've completed our first objective. We've quantified the harmonics in the cumulative air gap field and current linkage due to the stator winding. Next, we're going to relate these harmonics to torque ripple and rotor losses for three-phase machines. And this is going to be a pretty quick thing to do. So you can recall from our machine design sizing unit that we concluded that if the magnetizing field has the same harmonic component as our equivalent linear current linkage, we will create torque. And next, we concluded that our harmonics of our linear current linkage travel at different speeds. So some harmonics travel in the positive direction, others travel in the reverse direction, but the magnitude of the speed is always our electric frequency, that is our supply frequency, divided by our harmonic index times our number of pole pairs. And if we write our magnetizing field expression out as a Fourier series, so let's talk about an individual harmonic, we notice that all the harmonics actually travel at the same speed in this case, which is going to be omega by p. And so if you recall from our motor sizing unit, we came up with this expression for torque, where we had torque being 2 times the volume of our rotor times our average shear stress. And our average shear stress for an individual harmonic is equal to B delta peak times AV peak divided by 2 times the sine of phi I, where phi I is the angular spacing between our magnetizing field and our linear current density. And so if I paste in our diagram that we drew from our machine design sizing unit, we can look at the physical interpretation of all of this. So here we've got our rotor's position at angle theta, which is the distance to the North Pole. And then we've drawn on here our equivalent linear current linkage. And the distance between that windings axis, that equivalent linear current linkage axis, and the North Pole of our rotor is this phi I value. And so what we're saying right now is that we can draw this figure right here for every single harmonic. We could construct an equivalent number of poles on our rotor for harmonic 1, 2, 3, 4, 5, 6, whatever, any number. We can draw a rotor with that many poles. And then we've established an expression for our current linkage for that many poles as well. And so we can talk about the distance between the axis of that current linkage and our equivalent rotor. And that distance is going to be varying. It's going to vary because our rotor is always rotating at this speed right here, whereas our equivalent current linkage is always rotating at a different speed, omega divided by Vp. So what this means is that the sine of phi I is going to fluctuate. Phi I is not constant anymore. It's constantly ramping up and down because our waves are rotating at different speeds. And so this is what creates torque ripple. And so you can notice that it takes 2 to tango here. If we have a pure magnetizing field, that is, if V equals 1 is the only component of our magnetizing field, it does not matter how much harmonic content we have in our current linkage. It simply will not create torque ripple. So if V only contains a sinusoidal component at our desired number of poles, it doesn't matter what our winding factors are for anything other than V equals 1. We will create no torque ripple. But if both our magnetizing field and our winding factors have values when V is not equal to 1, and if those values line up, then we will create torque ripple. Next, let's talk about rotor loss. Okay, so the rotor loss is due to fields that are rotating at a different speed than the rotor, and we can calculate the losses in a piece of iron or a piece of conductive material as being approximately this expression. I'm writing this with a huge caveat. Whether these exponents are squared or they're times one, or they're to the 1.8th power or to the 1.5 power is something we're going to talk about in a separate video. But just know that the loss that's on our rotor surface is going to be a function of the magnetic field that fluctuates on that surface. And since our rotor is rotating at a different speed than the harmonics, we can see that if you were to stand on the rotor and look at the frequency components of the fields that you're going to see, they're going to be AC. They're not going to be DC because the different harmonics are rotating at different speeds. And we can calculate our harmonic fields from this expression right here based on our current linkage. And so this omega is a frequency that's observed by our rotor. It should not have a peak on it. And for a synchronous machine, that means our rotor rotates at the speed of our fundamental. It's going to be 0 for our fundamental. And then when we're talking about higher order harmonics, they rotate slower. So we're going to now have a non-zero omega. And some of the harmonics rotate in the reverse direction, which is going to give us a particularly large omega. And again, we will be talking more about this loss expression in a later video. So to summarize this video, we have first quantified the harmonics in our cumulative air gap field and current linkage. So up until now, we've been largely talking about air gap fields and current linkage of a single phase winding. Now we're adding all the phase windings together to talk about the total air gap field and current linkage. And then we've related these harmonics to torque ripple and rotor losses for three-phase machines. We've done this by deriving an analytic expression and then evaluating it at specific harmonics in a table form here. And we've noticed that these harmonics can travel in the forward or backwards direction or simply not exist, depending on which harmonic you're discussing, and that the harmonics travel at different speeds. The speed decreases as we go to higher harmonics. Finally, we've related this to torque ripple, where we've talked about the underlying physics that create torque ripple, and then we've related this to the losses that we experience on our rotor surface.